it's all been very interesting. And now if you'd just tell us what...
Wait a minute. I have a question. You have been splitting time smaller and smaller. Now, is there any limit to how small time can be split?
If there is such a limit, it would be shorter than the time it takes light, which is the fastest thing we know, to go across the smallest piece of matter, which is an atomic particle. This would be approximately 1/millionth of a billionth of a billionth of a second.
Well, they wouldn't want to split it any smaller than that.
Certainly they would. If they could. Wouldn't they?
Yes, if they could. You see, if there is a limit to how small time can be split, it would mean that time is not a continuous flow, but is made up of little pieces.
Little pieces of time. It's unbelievable.
That's because our feeling of time is limited. We can grasp only those intervals we're familiar with. Seconds at one end of the scale, hours, days, months, and at the other end, the number of years in a lifetime. This is a very small range in the middle of the vast scale of time. The infinitesimal fractions of seconds at one end and the billions of years at the other. We say that the age of the Earth is 4.5 billion years, but how long is that? Let's consider the life of the Earth in terms of what went on, what happened, what changed. Since it's difficult to relate our feeling of time to large numbers, let's squeeze the age of the Earth into one 24-hour day. We begin at midnight, 4.5 billion years ago. It's a long time, say 2 o'clock in the afternoon, before any life at all appears on the Earth. At 7 p.m., life begins leaving remains in the form of fossils. Dinosaurs develop at 11 p.m. Only 1 hour left to go in our Earth day. And now, at just 2 seconds before midnight, the human species first appears on Earth. In the last 1/10 of a second, the entire 6,000 years of civilization since the early Mesopotamians and ancient Egyptians takes place. And in the last 1,000th of a second before midnight, there are the 2 world wars.
But there's one thing that bothers me. If people weren't even around most of that time, how do they know what went on and when?
Perhaps a geologist should tell you about it. This is Dr. Gerald J. Wasserburg.
The events in our natural history and the times at which they occurred can all be told from rocks. By examining the fossils, the minerals, the makeup of the rocks, we can tell what happened and the sequence in which these events happened. By using radioactive elements as our clocks, we can answer the question, when did certain events happen? We know, for example, that in 4.5 billion years, 1/2 of the uranium in a rock turns into lead. By measuring the proportions of uranium and lead in a given rock, we can figure how long it took for that amount of lead to form. This gives us the date at which the rock solidified. In this way, we have been gathering information on the age of the Earth, its eras, and its epochs.
They see all that in rocks?
Yes, rocks hold the secret of our past. They're the only history of the Earth. It's all there in the rocks, waiting for man to discover. Some places, nature has given man an opportunity to see the changes that have taken place over vast periods of time by exposing a sequence of layers, preserving for us a long record of Earth history. Records that show there were once deep waterways where mountains now stand, large land masses that have been lost to the seas, and the Earth is still changing. The same forces that have changed the face of the Earth in the past are still at work. Wind, rain, rivers, glaciers, earthquakes, and volcanoes. How will the Earth look in the eons to come? If the Earth has a past of 4.5 billion years, what is its future? We can only guess, but the vast time of the past is small compared to the far greater expanse of time that is the future.
We've gone from a millionth of a billionth of a billionth of a second to billions of years.
Well, that certainly covers time.
Do you know what I like about time? It has order. It has mathematical precision. One can almost see time evenly flowing throughout the universe.
Very interesting that you should describe time that way.
Thank you.
That idea of time was accepted as scientific truth on Earth.
Very good thinking, sir.
Accepted, that is, until the beginning of the 20th century.
Just what do you mean by that?
Time is no longer considered absolute. It is not the same everywhere.
You mean that the same time here is not the same time there, and that the same time is not flowing everywhere?
No, I'm afraid it isn't. How does that look to you?
They're moving too fast.
How does it look now?
Too slow.
You mean that one group's moving slower and the other's moving faster than we are?
Well, yes, we're moving normally, but they're not.
But if you were with those people, moving at their rate of speed, either fast or slow, it would seem normal to you.
And I couldn't tell?
Not if everything conformed to that rate. The speed an object falls, that water pours, the speed you talk and think, everything. When we look at those people moving at different time rates, they look peculiar to us. They look peculiar to each other. And to them, people moving in our time rate would look peculiar.
Well, that was an interesting demonstration, but I still can't believe that in real life, time could flow at different rates.
The scientists have found that time rates are actually different under certain circumstances.
Well, under what circumstances?
Well, for one, the faster anything moves, the slower the time rate for everything connected with it.
You'd better tell me that again.
All right. Just imagine people traveling in a spaceship at almost the speed of light. They'd be living in a much slower time rate than we are.
They would, eh? Well, how did they figure that out?
It all began with a famous experiment made back in 1887 by two American physicists, A.A. Michelson and E.W. Morley. They wanted to measure how fast the Earth is moving through space. So they set up an experiment based on a simple principle we all know well from everyday experience.
We do.
Well, let me show you. Now, suppose we're in a moving car. A train going in the same direction passes us much more slowly than it does when we're going in opposite directions. In fact, the actual passing speed is simply the addition or subtraction of our speeds. It was this principle that Michelson and Morley tried to use in their experiment. Only instead of sitting in a moving car, they sat in their laboratory on the moving Earth. And instead of a train, they used light. By comparing the speed of the light in various directions, they hoped to measure the speed of the Earth.
Well, what happened?
There was no effect. The light seemed to travel in the same speed no matter which direction it was going. In other words, it looked as if the Earth is standing still.
That's impossible, isn't it? I thought it goes around the sun.
Yes, they've known that for 400 years. So scientists went right on making more experiments to detect the motion of the Earth through space, but none showed any effect.
How did they explain their way out of that one?
Among those who proposed explanations was a young clerk in the Swiss patent office named Albert Einstein. He said, of course the Earth is moving, but the laws of nature must be so constituted that there's no way to detect it or to prove you're moving without comparing or relating to something outside that isn't moving along with you. This is the principle of relativity.
Einstein's theory of relativity.
The first part of his theory, it's really not so hard to believe. For example, in a plane flying at a uniform speed without any bumps or turns, you can't tell you're moving without looking out of the window.
So, in order for Michelson and Morley not to be able to tell the Earth was moving, the light had to travel the same speed in either direction.
And that was the second part of Einstein's theory. He said that light would always be observed to travel at the same speed, no matter how fast or in what direction you were going.
You mean, if I were in a very fast spaceship, a beam of light would seem to pass me just as fast as it would you on the ground?
That's right. Sounds impossible, doesn't it? But Einstein explained it by pointing out that the only possible way that two people traveling at different speeds can both measure the speed of light the same is that their measuring devices have become different because of the difference in their speeds. And so they have different senses of time and space. For example, if you were in a spaceship, to me on the ground, your clock would seem to be running slower than mine.
Let's try it, huh?
All right. With some simple animation, let's see why the clock in a spaceship traveling near the speed of light and the clock on the Earth measure time differently. Now, here's a simple clock, a hollow, transparent rod, a mirror on each end, and a beam of light bouncing from one end to the other. The beeps tick off regular intervals, same as any clock. Now we have two of them. One is put in the spaceship, and one kept on the ground. To the man on Earth, his clock continues to run at the same rate. But when he looks at the spaceship going by, the action of the light in that clock looks like this.
I think I see what's happening.
Perhaps it'll be even clearer and slow. Because the spaceship is moving past the Earthman, the light appears to him to travel diagonally to get from one end of the clock to the other. Because the light goes further, it takes longer between ticks. And from the Earthman's point of view, the spaceman's clock is running slower.
The man in the spaceship must think his clock is crazy.
I would certainly think so.
Well, let's see. Inside the speeding spaceship, the spaceman looks at his clock. It seems perfectly normal to him, just like it did on Earth. His sense of time is different. Everything is changed proportionately, so that strange things would have had to happen. Weights would increase, lengths would change, all in perfect proportion, so that he wouldn't notice any change, and so that everything would seem perfectly normal.
Is it so important that everything seem normal?
Remember the first part of Einstein's guess? The principle of the laws of nature are so constituted that you can't tell you're moving without relating to something that isn't moving along with you. Then everything in the spaceship must seem perfectly normal, or else the spaceman could tell he was moving. With our light clock, it's easy to see how this effect increases as your speed approaches the speed of light. It's the same with everything in motion. But in our normal lives, we never get anywhere near speeds great enough to show this effect.
With our talk about that spaceship, is it possible that people may someday travel near the speed of light?
At the moment, it's pretty remote. But based on Einstein's theory, it's fun to conjecture what would happen. Here is a story of identical twins living in the Einsteinian future. Our twins, Peter and Paul. They're having an argument over who's to have the honor of being the first Earthman to travel to the distant star, Arcturus, and back.
I want you to have the honor. No, you deserve it. See you in 60 years.
Although Peter was 83, he didn't want to miss his brother's moment of glory. Yes, compared to his brother, Paul was still a young man.
He doesn't look 83.
He isn't. Traveling near the speed of light, he aged less.
Oh, yes. Time slowed down.
That's right. The closer he came to the speed of light, the more Paul's heartbeats, with their periodic motion measuring time, would slow down, along with his rate of breathing and other body processes. Paul wouldn't notice, though, because his watch would slow down to the same degree.
How do you know that Einstein guessed right and his theory is really true?
Well, let's ask a physicist. Dr. Richard Feynman of the California Institute of Technology.
In the laboratory, we can get atomic particles to go nearly at the speed of light, and so far, all the effects predicted by Einstein show up. For example, particles which are unstable and disintegrate do last longer when they're moving than when they're standing still. Einstein's theory of relativity has radically transformed man's picture of the universe. It has upset our traditional ideas about time and space. And someday we may upset them once again because we're still learning. What determines the direction of time? What distinguishes past from future? And what exactly is the present? Is now the same for everyone?
Doctor, is now the same for everyone?
No?
I was afraid of that.
Well, thanks for the use of the planet.
Oh, wait, please. You're not going to leave me now, are you? I mean, we've gone all the way from shadow on the ground to...
Sundials and pendulums,
and from atomic clocks
to suns, moons,
Stars.
from time that was fixed.
to time that is relative.
We've come a long way.
Yes. But now I have more questions than ever.
Good. The more we learn, the more questions we have. In the beginning, you had only one question. What time is it?
That's right. Well, where do I set the hands of the clock?
Oh, that. You can set them any place you want.
You mean because I'm the king?
No. Wherever you decide to set a clock in the beginning is more or less arbitrary. However, once you've set it, that becomes your time, and all your clocks must be synchronized.
Well, thank you.
Now we can set our clock. Sir?
Well, for our purpose, that sort of winds up the story of Planet Q. But the story of time is just beginning. Stretching before us are who knows what complexities, perplexities, mysteries. How did time start? We don't know. Did the universe begin with a big bang 10 billion years ago? Some physicists and astronomers think so. But others ask the question, did the universe even have a beginning? Or has it been going on forever? Will it ever? Some 20 billion years from now, when our sun burns itself out and explodes into oblivion, will time stop? Or will we just sit cooler and cooler, longer and longer, without light, without warmth, in the fathomless depths of space? These are questions which baffle astrophysicists, cosmologists, many men of science. Men whose minds and imaginations are even now uncovering clues to the mystery of time, which has perplexed mankind for centuries. What time is it? The answer may be phrased in terms of molecular action, the laws of nature. But more directly, what time is it is a question of our everyday lives, the contraction of our arteries in our lungs, the beating of our hearts, the measure of our todays, our tomorrows, our lifetime. As written in Ecclesiastes, to everything there is a season. A time to be born, a time to die. A time to plant, a time to pluck up. A time to cast away stones, a time to gather stones together. A time to every purpose under heaven.
The Bell system is grateful to the many distinguished scientists who helped prepare this story of time. Our thanks to those who supplied and checked the scientific content, and to the individuals and organizations who provided special material. Our thanks to the advisory board, which reviews the scientific aspects of these programs. Its members represent the broad range of modern science: biology and genetics, medicine, bacteriology and botany, chemistry, geophysics, physics, anthropology, electronics and acoustics, mathematics, engineering. To all these men, the Bell system is indebted for their support of this venture in public education through entertainment.